Well, thank you for inviting me to give this talk. And also, I'd like to thank the organizers for the great amount of attention that they paid to deciding the timing of this talk. It was originally scheduled for Monday, and then Thursday, and then Tuesday, and then Thursday, and there were a few more iterations, I think.
This is hypercyclical.
Yes. Anyhow, this talk does overlap to some extent with Ralph Schill's talk on Tuesday afternoon, but there are probably a few people in the audience who weren't here then, and there may sometime in the future be some people who watch this on video, so I'll try not to assume too much knowledge of Ralph's talk for the benefit of such people. So I'm going to start with a couple of example stroke applications before coming to the theorem that Ralph talked about. And so firstly, from damped wave equations, this did appear in Ralph's talk, but I'll give a bit more detail here. So one has a damped wave equation as given at the top of the screen here. Here's a damping term, and the damping term is a positive function, A, so this is genuinely damping and not actually increasing energy and so on. And we're working, well, I've expressed this on a smooth domain in Rn, but it could be a manifold more generally. And the damping function I've said is continuous, but that's not really completely necessary. And I'm assuming Dirichlet boundary conditions here. So H10 is the first order L2 Sobolev space, and 0 represents the Dirichlet boundary conditions. And then we have some initial values, and the energy of the solution is given by this formula. And it's easily established from the positivity of the function A that the energy is a decreasing function of time. And just a brief summary of well-known results from quite some time ago is that, well, excluding degenerate cases like when A is identically 0 and a few trivial cases of that form, the energy does decay to 0, and this can occur typically at various rates. So if the domain of damping, that's the set of x's in omega where A is strictly positive, if this satisfies something called the geometric optics condition, so this is something that depends on the geometry of omega and the geometry of this set where the damping is occurring, then the decay occurs at an exponential rate in time. And there are various other results saying that when this condition is not satisfied, the decay occurs at other rates, like polynomial in time or logarithmic in time. And these rates tend to be uniform for smooth initial data. So what's going to happen here is that we're going to look at rates of decay which are uniform for first-order smoothness. But if you know that, then you can deduce the rates for higher-order degrees of smoothness as well. Now, these questions can be approached by more than one method, but the method I'm going to concentrate on is the one that I know something about, which is reformulating the damped wave equation in terms of operator semigroups, and that involves working on the product space of the Sobolev space and the L2 space with this operator A, with this particular domain. So we have a second-order Sobolev space here, but we have a Dirichlet boundary conditions for the first derivative. And then if we write capital U to be the pair consisting of the little u, which is the solution of the originally damped wave equation and its partial derivative, The energy now is just essentially just the norm. This is the norm in the space X, so it's the first order subleft norm and an L2 norm. It's actually the energy is the square of the norm and conventionally multiplied by a half. But then our equation becomes, just in abstract form, a simple Cauchy problem, u prime of t is equal to a u of t with initial values. So if we can obtain general results about semigroups, we have a chance of applying them to this damped wave equation. Now, back in the 90s, Lebeau adopted this approach and showed, first of all, that the spectrum of the operator A is contained in a set that's given here. So this is actually shows that the spectrum is contained in a strip, but I'm not really interested in the left-hand side. I'm much more interested in the right-hand side, and in particular, that's a strict inequality. So there's no spectrum on the imaginary axis. And so the spectrum is contained in some region like this. It's very likely that the spectrum is not the whole of this, but is something much smaller, possibly even a discrete spectrum. It may be asymptotic to the imaginary axis, but it does not meet the imaginary axis. And the resolvent growth is at most exponential as you go along the imaginary axis, either upwards or downwards. He also showed that the damped wave equation is well posed, so that corresponds to A being the generator of a C0 semigroup, actually of contractions. The energy is decreasing. So then we have this Laplace transform relationship between the resolvent on the left-hand side and the semigroup on the right-hand side. And our function u is just given by the orbits of the semigroup. Now, these integrals are not really, don't work in operator norm. You have to work in the strong operator topology to define the integrals. So if we're looking for decay of energy uniformly for initial data in the domain of A, that's at first order level of smoothness, this corresponds to operator norm decay of TT with the resolvent at some point in here. It doesn't matter what point lambda we take. If we replace lambda by a mu, another point, this doesn't change up to a multiplicative constant. So for the nature of the decay is the same. And for most of this talk, I'll be able to assume that lambda is 0 and just write A inverse instead of this resolvent. And the next bit may be a bit invisible to you because it's catching on the... Just by hand? Oh, yes. So various people whose names are mentioned here found ways of passing from estimates for the growth of the resolvent on the imaginary axis to rates of decay. Lebeau started this himself, and then some people are named here, but there were others who are not named. So that's the first possible example or application. And now I turn to something quite different. I'm not terribly knowledgeable on differential geometry and so on. But it turns out there's a notion of Anosov flows on manifolds. Well, there's a notion of an Anosov diffeomorphism in the first instance, and then Anosov flows are just one-parameter groups of diffeomorphisms on a compact Riemannian manifold. And an Anosov flow behaves in, well, various ways of describing it. There's a sort of hyperbolic behavior on the tangent space of the manifold. Or there's what can loosely be called chaotic behavior. I'm not using the word chaotic in any of the technical senses that we've heard in this conference before. But basically, what's happening here on the manifold is that the flow is acting in an expansive fashion in some directions and in a contractive fashion in other directions. And this becomes hyperbolic behavior on the tangent space. And for a flow, in the direction of the flow, the behavior will be neither contractive nor expansive. So the tangent space actually has a decomposition into three, as a direct sum of three spaces. One being corresponding to the direction of the flow, one to an expansive, and one to contractive directions. And then it was known some time ago that this has mixing properties in this sense here. And people started trying to establish the rate of convergence in this limit. And again, there's another long list of names here reflecting various cases that have been established. The names of Rouel and Polycott are often associated with this because they started it, but the person who perhaps made the biggest advance in methodology in passing from just rather special cases to a more general theory was Dolgopiat. But if you try reading his papers, then it's not very easy, I believe, even for specialists to read them. And Dolgopiat's work was explained in a nice way, at least for me, by Liverani. So what's going on in this work of Dolgopiat is that a Banach space X is introduced, which is continuously embedded in the continuous functions and contains the smooth functions. And when one can look at the semigroup associated with the flow, actually this is a group in this case, but that doesn't play much role in this talk. So let's just take A to be the generator, so that's just the derivative. And then there are some arguments. First of all, there's a quasi-compactness argument. This is an argument which is similar to the notion of compact resolvent, but you don't quite have that much information. But you get enough to tell you that there is for these Anosov flows, there is a spectral gap. Now, of course, as things are at the moment, the constant functions are contained in the space X, so you get zeros in the spectrum here. But it's an isolated point, and the spectral gap says that the rest of the spectrum is away from the imaginary axis. In this case, the spectrum is not asymptotic to the imaginary axis at infinity. So then you can remove this point by just taking a projection and looking at the rest of the space. That's the space where the integral of the function with respect to the invariant measure is 0. And so then the mixing property now becomes convergence to 0. And then embedded in Dolgopiat's work is this estimate for the resolvent of the generator. But this is not a standard resolvent estimate, because here the power is not 1, and it's not even constant. It depends on the value of S, which is the imaginary part on the axis here. And so this power is growing slowly and logarithmically as you go away from the imaginary axis. Now, there are also other things here. The estimate is actually not on the imaginary axis, but it's shifted to the right at a point alpha. And then there's also a number minus lambda over here. And it turns out that by elementary methods, one can get from this estimate here to the spectrum, at least once you've removed this point, not having, not entering into a strip like this. And you also get a polynomial bound in terms of, well, mod lambda or mod s throughout this strip. So here you've got growth of polynomial growth, 1 plus mod s to the alpha, where s is the imaginary part. And over here you've got, well, just your basic Hiller-Yoshida estimate here, constant over the real part of lambda. Maybe I write lambda here, they're equivalent. And you also get, on the imaginary axis, you actually get logarithmic growth at the most. That's a general fact about holomorphic functions with this sort of behavior. In this situation where you have polynomial growth here and this estimate on the right half side, you get automatically, using harmonic measure if you like, you get logarithmic growth on the imaginary axis. Right, so that's the sort of background material that's involved here. Here is the Ingham-Karamata theorem that Ralph did talk about in a fair amount of detail on Tuesday. So this is formulated in the way that Ralph mentioned in terms of functions where you take the Laplace transform, and my functions are going to be bounded. So this exists on the right half plane, and I assume that the Laplace transform extends analytically across the whole of the imaginary axis. And then, well, this is a simple formulation. I just say that the indefinite integral converges to f hat of 0. Now, that formulation is fine for dealing with semigroups because the resolvent is analytic, and we can then obtain this theorem here, that if we have a bounded semigroup and we have no spectrum on the imaginary axis, then the norm of TT A inverse tends to 0 as T tends to infinity. So for the damped wave equation, that gets us back to the first of the standard properties, that the energy decays to 0. Now, once you've got that, it follows very easily that TT of x tends to 0. For all x's in x, you don't need smoothness here because this tells you it works for x's in the domain of A, and then density of the domain together with boundedness of the semigroup tell you this works for all x. And this is something that Wolfgang Arendt and I became aware of the best part of 30 years ago now. But we pursued this result in a different direction at the time. We concentrated on this property and weakening this property. But I'm not going to go into that on this occasion. So, for the rest of the talk, basically I'm going to be discussing bounded semigroups with generators A, and the spectrum is then contained in the closed left half plane automatically, and almost always I'm going to be assuming that actually there's no spectrum on the imaginary axis. So, as Ralph explained in his talk, one can in fact obtain estimates for the rate of convergence in the Ingham-Karamata theorem. And here is the result, which is similar to the one that he described, although again I'm assuming slightly more here than he did. So the assumptions now say that the Laplace transform f hat can be extended analytically to a domain which is defined by 1 over m, where m is some given function, continuous and increasing. So the distance over here is about 1 over m of s, if I'm at is here. And I'm also using here the same function m as an upper bound for f hat of lambda in this region. Then you get convergence like this, the reciprocal of the inverse of not quite the function m, but a logarithmic correction of m. So here's the definition of m log, and it's m multiplied by the log of m and or the log of s. And the little c here is an absolute constant. A quarter is certainly fine. The natural boundary for c would be 1. And I thought that it worked for little c equals anything less than 1. But David Seifert tells me that he doesn't believe it, except for c less than a half. Now, when you go to semigroups, it's natural for this to be measured by the same quantity as f hat is, because if you have the resolvent on the imaginary axis has norm m of s, then by Neumann series, you can extend it a distance 1 over m of s to the left or any other direction. So, well, I think one should regard this m as being twice the previous m. We arrive in this situation, and then we get that if we have an estimate for the resolvent of a bounded semigroup on the imaginary axis, we get the TTA inverse decays at this rate. What does this tell us? Well, first of all, let's think about the case when the resolvent is bounded on the imaginary axis. Then, by Neumann series, it's actually bounded a little bit to the left. The theorem I showed you tells you that TTA inverse decays in norm at an exponential rate. There's nothing new in this, because Weiss and Vrobel proved something much more general 20 years ago. It was much more general because they didn't even assume the semigroup was bounded. If you're in Hilbert spaces, there's an even older theorem from the early 1980s, the Gerhardt-Preuss theorem, that tells you under these assumptions, again for a semigroup that's not bounded, but for the resolvent bounded on the right half plane, including the imaginary axis, you actually get decay of the semigroup without the A inverse term in there at an exponential rate. So we were not learning anything new about this case of bounded resolvent. Let's go to another extreme when the resolvent grows exponentially fast here. Then the result of the Ingham-Karamata theorem is the norm of TTA inverse decays logarithmically. Now, what's happened here is that the logarithmic correction in the m log theorem, the log there doesn't come in. It gets swamped. And the inverse of m log has the same asymptotic behavior as the inverse of m when m is an exponential function. So we just get a nice 1 over log decay. Now, this was, to some extent, new. It wasn't new in the case of Hilbert spaces, because Burke had proved that exactly this result for Hilbert spaces in 1998. But it was new for Banach spaces, I believe. In between these two cases is the possibility of having polynomial growth of the resolvent on the imaginary axis. And then the m log theorem gives this form of decay, which is basically polynomial, But if you really care about the powers, that alpha in the inverse function would become 1 over alpha, and now we have a log t term coming in here. So this log t term comes from the logarithmic correction in the m-log theorem. Now, this result improves, even in the Hilbert space case, this result, I think, improved what people knew. There were some results of this type with a different power, a higher power of the logarithm on the top, on the case of Hilbert spaces, or with a higher power here for the general Banach spaces. Now, more recently, with Alexander Borochev and Yuri Tomalov, we've looked further at this, and we started considering LP versions of this M-log theorem. So that's one of the two enhancements that appear in this theorem. This is stated for any p from 1 to infinity. The previous case, p was equal to infinity. There's another change here, which is now, although I still use M to define the region where we can extend analytically, I don't assume that f hat is bounded by M. I assume it's bounded by M to some arbitrarily large power times the imaginary part of lambda or mod lambda to an arbitrarily large power. And then we get the same result, basically. So for p equals infinity, this would just be telling us that this estimate was less than constant over this function. So that would be the same result. Now, for convenience, I express this as saying this, for a general p, this function is in LP. So it's a weighted LP result, with the weight being this function. The value of c now depends on p to some extent, and it depends on alpha and beta. And as alpha and beta increase, c may get smaller and tend to 0. But the improvement here is telling us that the shape of omega m is really much more important than the actual bound on the Laplace transform in that region. The variation of p from infinity to 2 the slides are not in the same order as I thought they were. Let me go back to Anosov and Dolgopiat. With p equals infinity, m is a constant. Well, here's the picture for that. That's all right, because in the situation of the Anosov flows, we actually have a spectral gap here. So omega m, when m is just the constant function 1, still works. And then we had this at most polynomial growth here. That's all right because of the improvement in the bound, or the relaxation in the bound that was assumed. So we are able then, in the situation of Anosov flows, to obtain this sort of estimate, and then the enhanced version of the theorem tells us that we get decay, which is exponential. So this generalization, small generalization, enables us to bring the results within the scope of our theorem. Of course, the hard part of the whole business of Anosov flows is actually establishing the Dolgopiat estimates and finding the right space X in which to work. Now, you may wonder, does this log term, logarithmic correction that's been appearing from time to time, does it really have to be there? Here's a converse result. Suppose that we know that TT resolvent decays at some rate little m. I'm not assuming in this result that there's no spectrum on the imaginary axis, so I haven't written A inverse here, but that's part of the conclusion that if TT resolvent decays, then there's no spectrum on the imaginary axis. And moreover, you get an estimate for the growth of the resolvent in terms of the inverse of this function. So this tells us that we can't do better than something or other, and in the M-log theorem, it tells us that we cannot do better than replacing M-log by M inverse. That's the best possible result that one could get, and you may wonder whether we can always get rid of this logarithm and get this rate of decay in the M theorem. The M-log theorem would become an M theorem. And this question was, now that's got in the wrong place. This question was mentioned in a rather vague way in my paper with Dykert and answered very quickly by Borichev and Tomilov in the polynomial case. So they showed two things. One is the Banach space first case, and one is the Hilbert space case. And these go in opposite directions. So in the Banach space case, the M-log theorem cannot be improved. And that's in the strong sense that if you take any faster rate of decay, you can find a counterexample. So this here really is the best that you can expect if you are in Banach spaces. But if you're working with these polynomial growth rates, you can improve. If you're working on Hilbert spaces, with semigroups on Hilbert spaces, you can improve the result, and you can get rid of the logarithm. That's what they showed. So this was not so difficult. This was a complicated construction. The example is artificial. It's nothing like something coming from damped waves or any form of partial differential equations. So one question here that is still obscure is what happens when you have logarithmic growth of the resolvent. The M-log theorem tells you that you get decay at least like this e to the minus constant square root of t, and it's not really clear when this can be improved to get exponential decay, which would be what happens if one had an M theorem rather than an M-log theorem. That can't be done in full generality, but for example, what happens on Hilbert spaces, can one improve it on Hilbert spaces? I think that's not known, not to me at any rate. I might just go back to the slide that was in the wrong place. I moved it yesterday and I put it in the wrong place, apparently. So this is just an indication of why the LP version of the theorem might be vaguely useful. If in the damped wave situation, we know that the energy decays at a certain rate measured by a function m here, or its square, for all the classical solutions, for all the sufficiently smooth initial data, then we can, from the theorems that I've shown you, we can actually obtain an integral estimate for the derivative of the energy. Now, the energy is decreasing, so this derivative is negative. So this absolute value just means minus the derivative. And then with the weight m log inverse at some kt, this becomes a finite integral. So this is something about an averaged out version of the behavior of the derivative of the energy. And this is deduced from this, first of all, by using the necessary condition to get that the resolvent is bounded by capital M, which is this function, and then using the M log theorem for p equals 2 to obtain this. It's not quite straightforward. You have to do a few maneuvers, but it does work. I seem to have some time left. So I'll talk briefly about the regularly varying case. So this is a case which is a perturbation, if you like, of the polynomial case, where the resolvent now behaves like a regularly varying function, that is, something which is polynomial perturbed by a slowly varying function. Regularly varying functions were mentioned in one of the talks on Tuesday, and here's the definition. Well, here's one form of the definition, that these limits for any fixed positive number lambda, these limits of the ratios, should be lambda to the alpha, or that's the same as saying that m is s to the alpha divided by a slowly varying function where these limits are 1. I'm introducing the slowly varying functions because I need them a little bit in a moment. So typical slowly varying functions are logarithms to any power, exponential of log to the beta for beta between 0 and 1, or this strange function which is very, very slightly less than the function s. So slowly varying functions cannot increase as fast as s. They have to increase slower than s. They're not necessarily increasing, they might be decreasing. If L is slowly varying, so is 1 over L, and so on. I've chosen to put the L below here. That's an arbitrary decision, because I could replace L by its reciprocal. Now, with Ralph Schill and Yuri Tomilov, we investigated what happens if the resolvent growth is a regularly varying function, or at least bounded by a regularly varying function. So here I'm assuming that L is increasing, so this growth is slightly less than S. I'm presenting this in the case when alpha is 1, because if I put in the powers alpha, they would just distract you. I'm hoping that you will pay attention to the L's here rather than to the alphas, and suppress the alphas for that purpose. Then we were able to obtain a rate of decay, TTA inverse of 1 over T L of T. In many cases, this is the good result. It corresponds to 1 over M inverse. And if I go back slightly to the previous slide, that works in this case when L is log S to the beta, and it works in the next case if beta is less than 1/2. So this is an optimal result for those examples of slowly varying L's. It's also possible, by repeating this argument, to get the optimal result when beta, in the second case, when beta here is between 1/2 and 2/3, and then between 2/3 and 3/4. So in fact, we're able to get the optimal result in all cases of the second case, but not for this third example here. So that's the case when the growth is slightly less than S, the growth of the resolvent. And now we look at the other case when L is assumed to be decreasing to 0, so the growth is slightly faster than S. And in this case, we didn't get such a nice result because we couldn't completely get rid of the logarithm. We managed to reduce the logarithm from being log t to being log t to an arbitrarily small power. But we couldn't get rid of, still haven't been able to get rid of this epsilon here. And then there's a slightly different slowly varying function appears here. Sometimes it's the same or at least equivalent to the same as L. But it would be nice to find a way to get epsilon equals 0 in this result, for example. Now, there are some other cases when you have no chance of getting rid of the log in the m-log theorem. One case is when m grows very, very slowly, because you cannot expect to get decay of TTA inverse faster than exponential. Just think of one-dimensional example, the function e to the minus t. So if m grows very, very slowly, you need a log term in there, or at least something other than m inverse. Another case when you can't get rid of the log is if m grows rather irregularly, by which I mean m is assumed to be increasing, but it may be that m increases for a while and then stays more or less constant for quite a long time, and then increases a bit more, and then stays constant for a very, very long time, and so on. If you have behavior like that, you can't get rid of this logarithm. And you can show that just using multiplication operators or normal operators on Hilbert space. So that's why, assuming the growth is something like regularly varying, is a reasonable sort of approximation is a reasonable class of functions to consider. They don't suffer these disadvantages that would prevent the m log being improved to m. Well, I think I have a few more slides, but I'm not sure I need to talk about them. And rather than detaining you, I might stop at this point, I think.